Welcome to screencast number 3 for Unit 6, Lesson 3. And we are talking about high-mass stars. What is the life cycle of a high-mass star? Remember, we talked previously about what happens with low-mass stars, stars such as the Sun. But now we're going to talk about stars that are much more massive than our Sun. High-mass stars follow a different life cycle than low-mass stars do. High-mass stars become supergiants rather than giants. Following the supergiant stage, the collapse of the star's core at the end of the fusion process causes the formation of some very strange objects. These objects include supernovas, neutron stars, and black holes. The high-mass star becomes a supergiant, so I'm on the red heading. When hydrogen fusion in a high-mass star ends, other types of fusion begin that involve the fusion of nuclei into elements heavier than carbon. What happens basically is you've used up all the hydrogen and you've fused it and you've made helium. Okay, and helium is more massive than hydrogen. Well, then you start to take the helium and fuse it to make even heavier elements. Okay, and that's what they're talking about. The star expands to become a supergiant. Hydrogen fusion stage in high-mass stars ends much sooner than it does in low-mass stars. High-mass stars, they have a lot more mass to start with, but they actually burn through it at a faster rate, so they don't last as long as low-mass stars do. So, a star, for instance, with 10 times the mass of our Sun will become a supergiant in just 20 million years. By comparison, it takes 10 billion years for low-mass stars such as the Sun to become giants. Okay? Then the supergiant collapses, triggering a supernova. Okay, so a high-mass star burns through its hydrogen through the process of nuclear fusion, and then it expands to become a supergiant, a huge, swollen-up star. But eventually, that supergiant is going to collapse, and it's going to trigger a supernova explosion. So, in the supergiant stage, the high-mass star fuses larger and larger nuclei until all of its nuclear fuel is used up. The supergiant no longer generates the energy needed to keep its core from collapsing. Remember, a couple of screencasts ago, I talked to you about the fact that there were two forces that are balanced when a star is stable, and that is the first force is the crushing inward force of gravity, but that's balanced by the outward force due to the energy generated as a result of nuclear fusion. And when those things are balanced, the star is stable. But when you no longer have nuclear fusion going on, then you can't prevent the gravitational collapse that's going to happen. Okay, at this point, with no more nuclear energy or nuclear fusion to stop the gravitational collapse, the core of the star rapidly collapses, and a tremendous amount of energy is released. Basically, it collapses and blows itself to bits. Okay, this causes the collapse to halt and the supergiant to become a supernova. Okay? A supernova is basically a gigantic explosion in which a high-mass star throws its outer layers off into space. Okay? Those outer layers that are thrown off into space during that explosion is what becomes a supernova remnant. The core, however, remains. Okay? So let's go to the next page and we'll talk about what that core becomes. Okay, so the collapsed core of a supergiant star becomes a neutron star. So the core of a supernova continues to collapse under the force of gravity. And if you guys remember from our unit on chemistry, you know that normally electrons orbit the nucleus pretty far away from the nucleus. So that, remember, most of the volume of an atom is in the electron cloud. So there's a teeny tiny dense nucleus in the middle, and then there's this vast space around where the electrons are circulating. But in a neutron star, here's what's happening. Protons and electrons are smashed together to form neutrons. If you can imagine, so much gravity that the space between the nucleus and the electrons is actually squeezed out. Okay, so everything collapses to such an extent that there isn't even space left in the atoms. And electrons are forced into the nucleus, and when they're forced into the nucleus, they fuse with protons and produce a bunch of neutrons. Okay, so that's why it's called a neutron star. So the resulting neutron star is a small, incredibly dense ball of closely packed neutrons. A neutron star may have a diameter of only about 20 kilometers, yet it may emit the energy of 100,000 suns. Okay, neutron stars rotate very rapidly. Some emit a beam of electromagnetic radiation that can be detected every time the beam sweeps by Earth. These stars are called pulsars. Okay, a lot of times those are radio waves that are being sent out as the neutron star spins rapidly. Okay, so that is a neutron star. What happens to the most massive of the massive stars? Something even stranger happens to those. There are stars that are so massive that their cores continue to collapse under the force of gravity. Okay, we've already squeezed out the space that was in atoms, but as unbelievable as it sounds, the core continues to collapse in on itself. The mass of the star is compressed into a single point, and this point is called a black hole. A black hole is an invisible object with gravity so great that nothing, not even light, can escape. Meaning, you would have to, like, to escape the gravitational pull of a black hole, you actually have to be traveling faster than the speed of light. So not even light gets out. Okay, that's why it's called a black hole. It's not actually a hole, it's an object. Though black holes are invisible, because light can't escape from them, they can be observed by the gravitational effect they have on their surroundings. Matter is pulled into a black hole. Think of stuff that's circling the drain as it goes around and around before it ultimately falls into the drain and disappears. It swirls around the black hole just before being pulled in. The matter becomes so hot because it's accelerating and being pulled gravitationally that it emits X-rays, and astronomers use the X-rays and other means to locate black holes, even within our own galaxy. All right, so let me show you what I've got for these 2 pages. Okay, you can see that high-mass stars follow a different life cycle than low-mass stars do. High-mass stars become supergiants rather than giants. Red heading that says high-mass stars become a supergiant. When hydrogen fusion in a high-mass star ends, other types of fusion begin that involve the fusion of nuclei into heavier elements, heavier even than carbon. And the star expands to become a supergiant. Okay. A little further down, a star with 10 times the mass of our Sun will become a supergiant in just 20 million years. By comparison, it takes 10 billion years for low-mass stars such as the Sun to become giants. Okay. Under the heading Supergiant collapses, triggering a supernova, find the sentence that says, the core rapidly collapses and a tremendous amount of energy is released. And then a little further down, a supernova is a gigantic explosion in which a high-mass star throws its outer layers into space. Okay, so what's left of the star after the supernova explosion? The core of a supernova continues to collapse under the force of gravity. Its protons and electrons smash together to form neutrons, and the resulting neutron star is a small, incredibly dense ball of closely packed neutrons. Neutron stars spin very rapidly. Okay, and here's your definition for a pulsar, which is one of the things that I added to your vocabulary list. If you will look at 13. What is a pulsar? A pulsar is a rapidly rotating neutron star. Okay. Then the red heading that says the most massive supergiants collapse to form black holes. There are stars that are so massive that their cores continue to collapse under the force of gravity. A black hole is an invisible object with gravity so great that nothing, not even light, can escape. Though black holes are invisible, they can be observed by the gravitational effect they have on their surroundings. Okay, I made some notes. Up here, for instance, a neutron star is a tiny star. but it can contain 1.4 to 2 times the mass of our sun collapsed into a super-duper small area. Okay, down here, a black hole isn't really a hole, it's an object that is super dense. Okay, black holes can't be seen directly, instead black holes are observed by the effect that they have on their surroundings. Okay, the last thing that I want you to do for this lesson is go to one of the pages that you have some room to write some notes. I know that you used one of them for your vocabulary, but find the other one. Okay, all your stars basically form from nebulas, some sort of star-forming nebula. Remember, we've talked about dark nebulas, emission nebulas, and reflection nebulas. Those are all types of star-forming nebulas. So they start out as a huge cloud of hydrogen gas that collapses in on itself due to gravity and forms stars. Stars with a low mass, while they are fusing hydrogen, they are considered a main sequence star. You'll understand what main sequence means in the next screencast. Where they spend most of their life. Eventually, they deplete their hydrogen resources and they turn into a red giant. After the red giant phase, the core collapses gravitationally and we get a white dwarf, and the outer layers float away and form a planetary nebula. That would be the fate of our sun, for instance. Okay, it's a relatively low mass star. Then we have high mass stars. While they are fusing hydrogen, they are considered a main sequence star. Then they swell into a supergiant while they are fusing heavier elements. They blow up in a supernova explosion. The core that is left collapses gravitationally, forming a neutron star. And then all of the outer layers that were blown off form a supernova remnant. Then we have what happens with the highest of the high mass stars. Main sequence star forms a supergiant when you are done fusing hydrogen, forms a supernova, and then collapses and forms a black hole.